At this time, I'd like to introduce our first presenter, Morgan J. Hurley, who is a project manager for Aon Fire Protection Engineering. Morgan, the floor is yours.
All right, Dave, thanks for that introduction. So today we are going to talk about aspirating smoke detection with a focus on harsh environments and extreme temperatures, and I'll define in a little more detail precisely what we mean by harsh environments and extreme temperatures in the coming slides. Just to give you an overview of what we're going to talk about today, our learning objectives for today's webinar. We hope at the conclusion of this webinar you will have some familiarity with operation of aspirating smoke detection systems, the components of an aspirating smoke detection system, application of aspirating smoke detection systems in extreme temperature environments where extreme temperatures might be either high temperatures or low temperatures. Again, I'll define what we mean by extreme temperatures in a moment. And then also we will talk about application of aspirating smoke detection systems in dirty environments. We'll also give you a little bit of an overview of available technology. So let's get right into it. What I want to do first is give you an overview, a very brief high-level overview of aspirating smoke detection. For most folks this will probably be somewhat of a review, so I'll go over it quickly. So basically what we have in an aspirating smoke detection is a network of piping throughout our protected space. That network of piping has holes drilled into it, which basically serves as the detection points. Those are the sampling holes through which air is continuously drawn. Then that air passes through a network of piping, through a filter, and then into a high sensitivity sensing chamber. Okay, and that's where the smoke detection actually occurs, is in that high sensitivity smoke detection chamber. There's a fan obviously that keeps it running constantly, and then exhaust is blown out of the detection unit. Generally you want to pipe the exhaust back into the protected space to prevent a potential pressure differential between the protected space and the area in which the detection unit is located. There's a couple different pipe configurations that you can use, and really what piping configuration you select is a function of what you're trying to accomplish with your detection technology, and then also the size of the protected space. So at the simplest, you can have a single pipe that connects into the air sampling detection unit. That's the first image at the top. And then as you can see, you can have multiple branches. And what we've shown here actually only connects into one sampling port in a air sampling detection unit, even though the bottom image has 4 different sampling runs. You could also have up to 4 individual branches that individually connect into a detection unit, which provides a fair amount of flexibility. The piping in the protected space could be at ceiling level, it could be in racks, it could be run vertically, for example in an atrium where stratification might be a concern, and so forth. In general, this piping is about 3/4 inch Schedule 40. In general, shorter pipe runs perform better than long pipe runs, and that's basically just a kind of like a friction loss problem. You want to make sure you're getting about even flow into all your sampling ports. You want your branches to be balanced for the same reason, so that you don't get preferential flow through one branch versus the others. And then I just want to briefly talk about detection principles, because that is relevant in the context of what we will call dirty environments in a moment. So there's 4 different detection principles that can be used. Basically filtered laser-based systems, just what the name says. Basically, there's a filter before the sampled air reaches the detection chamber. That filter removes large particles from the air, and then what's left over passes in front of a laser, and then the scattering from the laser onto the smaller particles that remain is analyzed to determine if it is consistent with a smoke signature. And then non-filtered laser-based systems, or also known as particle counting, uses a laser light source as well. However, there's no filtering of the air that occurs. Air goes right into the sensing chamber. And again, laser shines a light onto that sampled air, and the scattered air once again is analyzed, or the scattered light, I'm sorry, is analyzed. And an algorithm can distinguish between patterns associated with potential nuisance sources or dirty sources versus actual smoke particles. Cloud chamber is the oldest available or the original aspirating smoke detection technology, where basically there's a sensing element in a sealed chamber that has a high concentration of water vapor. When a smoke particle interacts with that dense water vapor, the particle of smoke is ionized, and then that ionization causes the water vapor to come out of solution, and essentially it comes out of solution with the air in the vicinity of the smoke particle, which effectively increases the shadow size of that smoke particle. And then lastly, a dual source sensor, which uses one LED source to detect low concentration of smoke, and then an infrared laser to identify nuisance sources like dust or other large particles that are not consistent with a fire signature. All right. Talk about alarm sensitivity for a moment. First, alarm sensitivity is adjustable. That is something that as a designer you can pick. What I've shown here is arbitrarily selected hole sensitivity of 2.5% per foot to be consistent with the sensitivity from a standard spot type detector. Basically, the holes in the sampling pipe are the detection points in the protected space. You get a little bit of additive effect if there are multiple holes that are entraining smoke from a fire, which results in an effective increased sensitivity for those holes where smoke is being drawn in. Important to keep in mind that there is a transport time. Basically, any air that's drawn into a detection port is going to take some time to travel through the pipe network and then into the detection chamber. The sensitivity per hole is user configurable. It can, you can achieve a sensitivity on the order of about 1,000 times greater than a traditional spot type detector, or if you want to go in the other direction, you can go about 3 times less, or I guess 1/3 less sensitive than a traditional spot type detector. Again, as the designer, that is something that you can select. All right, so brief introduction. What I'd like to do now is jump into the section of the webinar on extreme temperatures. So first, definition. What do we mean by extreme temperatures? Well, any listed conventional detector is listed to operate within a defined range, and basically as part of the testing process during the listing, the conventional detectors are confirmed to operate within the specified range. Essentially, that range is between 32 degrees Fahrenheit and 100 degrees Fahrenheit, or 0 degrees C and 38 degrees C for those who prefer SI units. If you have a application that is outside of that temperature range, then a conventional detector would likely not be suitable. But that doesn't mean that you can just throw in an aspirating type of detection system without thinking about it, because the temperature of the air in the sensing chamber of an air aspirating detection unit still has to be within a specified range. That range is generally manufacturer dependent, so something that you would need to check on. Essentially what you would need to do is, if you have an application where the temperature is either below that range or above that range, you would have to make sure that the air that's sampled is within that temperature range, or that acceptable temperature range, by the time it reaches the sensing unit, and I will talk about that in a moment. So just a couple examples of what we mean by extreme temperature environments: cold storage, where you might have foodstuffs that are stored at a very low temperature to maintain essentially freshness and so forth. Or at the other end of the extreme, a data center where you have a high heating load from the computational equipment, and essentially you wind up with a hot aisle where your temperatures could be outside of that acceptable range. A key concern in any time you have these temperature variations, and then you're trying to bring the temperature of the sampled air, either by virtue of warming or cooling, to another temperature, you have to be careful that in the process you don't cause essentially condensation to form inside of the piping, or if you do get condensation, make sure you can deal with it. And I'll talk about that in more detail in a moment. So a couple applications for refrigerated areas. Essentially what I've shown here is the gray portion is a refrigerated area, and then in this case the air sampling detection unit where the detection occurs is located in a non-refrigerated area. So basically there's a network of piping in the protected space, which here is a refrigerated area. Air is sampled from within that protected space and then brought to the air sampling unit, which is outside of the protected area. Any penetrations essentially into the freezer have to be properly sealed to make sure you don't get airflow from one temperature into another, which could result in buildup of ice. Essentially, again, you need to make sure that by the time any sampled air reaches that detection unit, it is within that acceptable range. And there's two ways to do that. One is essentially take advantage of a long pipe run where you get convective cooling or heating of the sampled air as it passes through the conditioned space, or you may need to put in some kind of heat trace or heat tape or the like. I'll talk about that more in a moment. So you also have to think about the sampling pipe materials that you're going to use. Typically sampling type detection units or systems use either PVC or CPVC piping. As you can see, those are only good to about 15 degrees below 0 Fahrenheit or 26 degrees below 0 Celsius. So if you have a protected space that has a temperature lower than that 15 degrees below 0 Fahrenheit, then you're going to need to resort to a different piping material for your sampling pipe. And I've posted here a variety of different materials that are options for you. As you can see, copper gives you the greatest flexibility in terms of temperatures. Of course, the downside for copper compared to the other materials is cost. But ultimately, you need to make sure that the pipe you select is suitable for the protected space. All right. So here is a example of a sampling pipe installation. So basically what I've illustrated here is a penetration of a ceiling and then the air sampling detection unit outside of the protected space. So if you do use metallic piping like copper for your sampling piping, you need to make sure it's properly grounded, because as air is drawn through that piping, a static buildup could occur. So that's why the piping needs to be grounded. Any penetrations into your protected space, again, need to be properly sealed to prevent flow of air from either into or out of the protected space that could cause buildup of ice to occur if it's a freezer. All right, you also have to be careful about pipe thermal expansion. I'll expand on that, pardon the pun, in a moment. In that generally when you install the sampling piping, it is installed at ambient temperature, not at the refrigerated compartment's operating temperature. But then as the space is refrigerated as it goes online after the detection unit's been installed, then there can be thermal expansion. All right. Again, if you don't have enough length of piping to allow the sampled air to be heated convectively as a function of passing through the protected space, and you might need some heat trace or heated cable to make sure that the sampled air is within that acceptable range. Okay. Also, unlike other applications, you generally would like to have the sampling ports in the protected space on the side of the pipes instead of at the bottom, and that is essentially to avoid the potential for frost buildup or ice buildup in the sampling piping. All right. Ceiling and wall penetrations. So generally it is preferred to penetrate through a wall as opposed to through a ceiling. And I'll explain why in a moment. Essentially, a lot of these decisions are driven by a concern for condensation forming for air vapors to essentially come out of solution with the air and then enter into the liquid phase, and then you've got to do something with that vapor in general or that liquid. But then if the air temperature is below freezing, then that liquid vapor or that liquid that comes out of solution could ultimately freeze, and then you have potential buildup of ice inside of your sample piping. All right. If it is impossible to avoid ceiling penetration, there's a couple things that you'll probably need to do. You want to make sure that your piping is insulated well in the vicinity of that penetration. Also, again, as with any penetration, make sure it's properly sealed. But then also include additional pipe insulation on the pipe outside of the sampled space. The reason is you're drawing cold air from inside your refrigerated compartment and then into an area which is probably approximately normal room temperature, right? So if that as you are in areas close to the penetration, because of the temperature of the air, the pipe temperature is probably below the dew point of the water, or excuse me, the dew point of the air. So you get condensation. You want to avoid that condensation because then it could drip onto the ceiling of the refrigerated compartment. And then if you do have to have a ceiling penetration, you probably want to put some kind of drip tray to catch that water that condenses onto the sample piping. All right. Thermal expansion. So anybody that's taken mechanics and materials remembers fondly thermally induced expansion. That's the amount of expansion that you get is a function of the pipe material that's used. Again, generally the sampling piping is installed at normal room temperature, right? But then as the freezer comes online, the temperature can drop, and it can drop quite a bit, right? So you have thermal contraction that occurs. You want to make sure that that thermal contraction does not potentially cause your sampling pipe to crack. So you generally would put in something like this U-bend that I've shown here to allow some movement as the pipe expands and contracts, most likely over the life cycle of that piping. That freezer is going to be warmed and cooled repeatedly for maintenance and so forth, so you want to make sure that the piping can handle those changes in temperature. Lastly, you generally would want to do a final integrity check on the piping at the freezer's operating temperature, just to make sure that no cracks occurred as a result of that thermal contraction as the freezer came online. All right. Also, when you're locating your sampling holes, you want to be careful of areas where there's direct contact with discharge air from the chiller. The reason is that the discharge air from the chiller can be much colder than the operating temperature in the freezer compartment, and that colder temperature might actually cause frost or water vapor to come out of solution with the air, or to condense out of the air in the sampling piping. So if it's impossible to avoid direct contact with that chiller discharge, you would want to insulate the sample piping in the vicinity of that discharge to minimize the cooling effect on the sampled air. Again, make sure your holes are positioned sideways. And you also want to avoid locations that are near things like doors where warm air may enter, because that warm air may have a dew point that is below the operating temperature of the freezer. So as that warm air is drawn into the sampling pipe by perhaps just opening a door, then you could wind up with you could wind up with condensation inside the pipe that could freeze. As with any aspirating type of detection system, it's a good idea to locate sampling ports near return air vents, because that's just the way air is going to naturally flow as a function of the HVAC system. And then lastly, you can use silicone spray to reduce water buildup on the sample ports. All right, so this slide shows a pipe trap which basically can collect water vapor if there is some in your sampling pipe, which this functions a lot like a P-trap like you might find in a plumbing system, where basically on this slide the piping from the protected space is coming in on the right. It then comes down and then branches off into a horizontal run. There's a slope on that run to allow any condensation to run back to that essentially drip loop, which functions like a P-trap. And then you want to keep some water in that drip loop to ensure that air isn't drawn in from the bottom of the drip loop. And then ultimately you can connect into a sampling port on the bottom of the detection unit to prevent or mitigate the potential for water vapor being drawn into the sampling unit itself. I mentioned that you need to bring the sampled air within the acceptable range of the detection unit in terms of temperature. If you have a long enough pipe run in your sampling pipe, then you don't need to do any supplemental heating. You can just take advantage of convective heating that occurs as the air is drawn through the pipe in the conditioned space. That might remind you of a heat transfer problem that you might have done in an undergraduate heat transfer class, but fortunately we've got some tables and charts for you where basically it's a lookup problem where depending on the flow rate through the piping and the length of the piping, you could figure out how much the temperature is expected to change as a function of the pipe length. And then lastly, you have to pay attention to the pipe support spacing when you have a refrigerated compartment, and that's just a function of, again, the potential for thermal expansion or contraction. You want to make sure that the piping can move freely within the pipe support so that there's no thermally induced stresses. And again, we've provided some lookup tables where we give you the thermal expansion coefficient for the different piping materials, and then we even do the math for given runs where you could figure out if you have a pipe of length X, what would be the expected thermal expansion or contraction, again as a function of the pipe material because that is material dependent. All right, so that was cold. Just want to briefly talk about at the other end of the extreme, hot aisles, where essentially what we've shown here is you might have some computing equipment which has a high heating load. Conditioned air comes in from the bottom and then removes heat from the computer equipment. By the time that conditioned air reaches the top of the space, it might be outside of the acceptable operating temperature range of a conventional detector. So again, this is a potential application for an aspirating type of detection system where, so here basically what you would need to do is sample air from that hot aisle. Again, you want to make sure it's going to be cool enough to be within the operating range of the air sampling detection unit. So the type of calculations that I mentioned before. The concern here is obviously as that heated air cools, if it's brought below the dew point of the air, then you can have condensation. Okay, so one thing we do want to mention is if you have an application like this, if you have an aspirating detection system that's going to be installed in a subfloor area, generally you want that to be a separate system from the one that protects the hot aisle just because of potential temperature differentials. All right, so we've got a little survey for you here that just to kind of close the issue of, close the subject of extreme temperatures, and then we will next move into dirty environments.
All right, great. Thanks, Morgan. This is where we would ask to get some involvement from everybody. Just have a quick poll question here. Your input would be greatly appreciated. In your experience, what factors lead to challenging applications for providing smoke detection? We have temperature extremes, difficult access, excessive airborne particulate, large open spaces, and then the last one is hot aisle, cold aisle. We'll just give some time to let everyone put in their answers. While we do this, I'll take this opportunity to ask a question and share with the group the answer. One of the ones that had come in, it says, are there any NFPA test and inspection forms for this type of system? If Nick or Morgan, if you could answer that.
Well, I would, I mean, just a general question that, yes, certainly NFPA 72 would address inspection, testing, and maintenance in the same manner that it would in any type of a detection system.
Great, thank you. All right, we'll get back into the presentation. So Morgan, here we go, dirty environments.
All right, thanks. So dirty environments. You might ask yourself, why would you cover dirty environments in a webinar that also covers extreme temperatures? And the reason is that there's a lot of common techniques that are used in these two different types of applications. So what do we mean by dirty environments? It could be like a waste transfer center where trucks come in and dump municipal waste while it awaits transportation to a dump or recycling center. Could be a zoo or a stable where animals are present, manufacturing or industrial facility, motor control room, or a area where chemical vapors could be present. All right. So just a couple of limitations of spot type detectors in these dirty environments. Dust or dirt could cause nuisance alarms, or it could cause dust or dirt could cause a dirty detector warning. Ultimately, it could dust or dirt could damage detectors, or just cause drift in a detector that is designed for drift compensation. Benefits of aspirating smoke detection systems in these environments. Aspirating detection system can differentiate between dust and dirt and smoke, allows for early detection. We can put our air sampling device unit in a clean location so that just the pipe is in the potentially dirty location. And then we can also clean our piping remotely by using a vacuum or a blower. All right, so basically it may be necessary in these dirty environments to provide an additional filter to remove particulate from the sample air. Most of the problems that occur with these systems in the field occur due to improper maintenance, where if you have a dirty environment and dirty air is continuously being drawn into your air sampling type of detection unit, if it's not maintained, then you can have a high buildup of dirt and debris. So a way to alleviate that potential issue is to install an isolation valve, where essentially what you do is isolate the detection unit from the sampling piping, and then if you put a T connection in, you can remotely clean the piping in the protected space by using either a vacuum or a blower. Again, moisture control can be a concern, particularly here. I'm located in the Washington, D.C. metropolitan area, where summers can be very hot and humid. If you have your detection unit in a conditioned space and you're sampling air from an unconditioned space, as that air is drawn in from the protected space and near the and then into the conditioned space, again, condensation can form. So you want to make sure you have a means to prevent that condensation from being drawn into the air sampling detection unit. You might use this kind of drip loop arrangement that I described on a previous slide. Okay, so some application-specific information, waste transfer or waste handling centers. So how would you design your air sampling detection system there? Basically, you'd want to put your air sampling detection unit in a clean location, like an office area or something like that. Provide a filter and three-way valve like I showed on a previous slide. And then install the sampling pipe at ceiling level, but make sure it's going to be clear of any moving equipment to reduce the potential for pipe damage during normal operations. Then, as with any other type of sampling type detection system, it's beneficial to put sampling holes near exhaust vents to take advantage of the airflow that already occurs within the space. You may need to provide vertical sampling pipe runs if there's a tall ceiling, particularly if there's potential for a high solar load that could cause stratification. And also, if you have an on-site incinerator, you may need to provide a reference detector, where basically what you're doing is you're separately measuring the smoke that is occurring from incineration, and then you are comparing the readings from the air sampling detection unit that's drawing air from the protected space with that of the reference detector to make sure you reduce the potential for nuisance alarms. In essence, what you do is subtract off that background smoke level that occurs from the incinerator doing its job. All right, zoos and stables. A couple other challenges in these types of locations where your concern might be tampering from the animals themselves. So again, put the air sampling detection unit in a clean location. Provide a filter to remove dust and debris. Conceal a pipe to avoid tampering by the animals. You might, if you have metallic pipe, you might even weld it to the cage itself to prevent tampering from by the animals. You might want to put sampling pipe in your return air ducts to take advantage of the HVAC airflow and so forth. So just some application-specific information there. And then lastly, for some other applications where you could have potentially dirty environments, manufacturing or industrial facilities, you might want to have early warning. You might use a detection system to activate a suppression system. Spot type detectors may not be appropriate in these types of applications. So in any event, you may also have concerns with access to spot type detectors if you have a high ceiling space. It might be difficult to get to them. Or you may also have concerns about a critical piece of equipment that you want to protect. All right. If you have an area where there's potentially combustible dust, you may need to have intrinsically safe detection systems. Also, you have to be careful to filter out the dust before it reaches the detection system. Similarly, if you have chemical vapors, you want to check to make sure that the electronics of your sampling device are compatible with those vapors that might be present. And again, you may have concerns with intrinsically safe systems. As I understand it, there is technology available now which is suitable for Class 1 Div 2 applications. And then lastly, just to talk about motor control rooms, you may have a room that contains these motor control units. Essentially what you have are a bunch of individual cabinets in a larger space. Those cabinets are almost sealed so that if you have a fire in one of those cabinets, it can burn undetected within that cabinet because smoke doesn't escape into the protected space. So in such an application, it might be desirable to provide individual sampling holes in the cabinets themselves. So anyway, brief overview there of dirty environments. I'll now turn it over to Bernard.
Thank you, Morgan. Good afternoon, everybody. Just a few minutes that we'll spend on how does FAAST actually deal with harsh environment. So at your disposal, all three units that we have, from the smaller through the medium to the big one. The small, just a reminder, 5,000 square feet, around 500 square meters. XM, the medium one, up to 8,000 square feet, and the large one, 28.8 thousand square feet. At your disposal, you have this configurable sensitivity levels, which you can use to suit or to tailor to any application, because the harsh environment usually requires an approach that is closer to fire risk management than just detecting fire. So you have from 3 to 5 programmable sensitivity levels, programmable delays, where you also might incorporate into your design, and then working with the configured thresholds, you can always work them to override the delays if necessary in the pre-alarms, at the pre-alarm stage. Obviously, for easier maintenance or easier installation, you have the top or bottom entry. As Morgan mentioned, especially when there is a humid environment, it's much more easy to use the bottom entry to use the water traps. For the acclimate mode, this is what we use when you have the ambient environment where there is a considerable amount of dust or sometimes even smoke, like from welding, etc. And then obviously you have all types of communications, either through the old school relays, through the TCP/IP, etc., or communications through the protocol to the panel. Now, how do we do it? How do we deal with this harsh or challenging environments? Well, first of all, we use the 3-stage filtration to deal with the nuisance or dust particles. And what we offer is this best-in-class immunity to false alarms, but using first and foremost the particle separator. This is the part on your right-hand side. I'm trying to mark it now so you can see it very clearly. So this pre-filters the air which may carry larger or any type of particles, and any larger particle will just drop down and it will be exhausted into the air again before even going to the field replaceable filter, which is that element here. It sits after the particle separator. This element takes care of any particle that is larger than 30 microns. And only then, when this air is duly pre-cleaned from, let's call it debris, from larger elements to particles larger than 30 microns, it goes into this third stage of filtration, which we call like dual vision filtration by light, where we have two independent sources of light, the red infrared laser and blue LED. Blue light, very short wavelength, is responsible for detection of practically every particle that is small enough to go through the chamber. The red infrared laser then enhances the accuracy of detection by finding all the larger particles that pretend to be smoke, but in fact they are dust particles or nuisance particles. So with this dual wavelength and dual angle approach, not only does FAAST offer the most accurate detection, but also guarantees the kind of like best-in-class immunity to potential false alarms. Now, on top of it, of course, there are advanced algorithms that deal with interpretation of the particles that go through the dual vision chamber. At the end of the day, you have the peace of mind that any nuisance alarms will be rejected as a false alarm, and the proper alarm will be then notified either to the panel or to a BMS system, depending on where your unit works. To support the hardware, let's call it the technology, we are also using the Pipe IQ software, which allows you to design the system and to configure the system, and that's especially important for harsh environment, to actually deal with different scenarios or different environment which the harsh environment or humid environment can cause. So as we usually refer to fire 1 as the alarm threshold which triggers the alarm, we should always configure it as low as possible for a given class, but not lower. The reason for it, you have a number, 1 or 2 pre-alarms or even 3 pre-alarms that you can use as a forewarning if there is an incipient stage of fire, even in such environment as harsh or humid. And then when it comes to fire 1, as of NFPA, for example, 72, the level of obscuration produced by smoke will trigger the proper alarm. The earlier thresholds can of course be set more sensitive, so you have that room to play with to actually deal with any kind of situation, depending on how much time and how quick you want to respond to alarm conditions. Just like I'd like to add literally a few items, a few projects that you might have or you will come across to add to Morgan's presentation about, for example, the elevator shafts, which is usually not only the harsh-ish environment, but also very often creates the pressure differentials where normal detectors might have a problem with dealing with. The attics, which are usually a harsh environment, dusty environment as well as food processing facilities or food processing plants, where not only do you have sometimes, not always, harsh environment, but first and foremost, even in such low temperatures of like around 40 degrees Fahrenheit or 8 degrees Celsius where they operate, the vapor carrying so much grease may clog the holes. And one very important thing, please do not forget that the aspiration system is just about the unit, the aspiration unit. It's also about the pipes and the hose. So as soon as you have the warning about the necessary cleaning or change of the filters, please do remember that the pipes and the hose need to be clean as well. And just to repeat what Morgan said before, use the use of purging system or blowout system. Please use them and make sure that you have those sampling pods clean as well, because otherwise the air will not be able to be drawn into those pods and then transferred or transported to the unit for proper detection. And just one last slide before we go into survey is a summary of what FAAST can do for the harsh environment. So first and foremost, apart from the accurate performance in terms of detection, the most important thing is the immunity to false alarms, which is the nuisance rejection technology that we use with the 3-stage filtration. Then we have the dual vision detection, and of course the flexible programmability, which will tailor any kind of configuration to the project that you may be dealing with in your professional life. So that's it from us. Now we'll just go into a very short survey and probably spend a few minutes, if we have still some time, towards the questions from the audience.
Yeah, thank you, Bernard. So this is the last poll question that we have. Again, your input is greatly appreciated. We want to know how else we can help you. Some of the options are: send me the FAAST data sheets, send me the FAAST product brochure, send me the Aspiration app guide, schedule a FAAST demo in my office, help me with the design, and then the last one is have a sales rep contact me. So again, your input is greatly appreciated, and it looks like we got about another 12 more minutes left, which we would like to do a Q&A. Nick Gomez has done a great job answering questions as they've come in. Krista Poss, our marketing leader, has also stepped in to answer some of the questions. So why don't we go through some of the questions that have come in, and we can share those answers with the group. One question I have here is, can this system be tied into an existing FACP, a fire control panel, or is it a standalone system?
So the answer is yes. Certainly can be. Actually, in the US, it has to be connected to an existing fire alarm system. It cannot work as a standalone system. We have two types of variants: the conventional, which can be connected to any conventional or any third-party panel, even addressable or intelligent. But also, on the other hand, we have a number of OEM addressable or intelligent variants, which are compatible with either Notifier or Honeywell or Gamewell or several others that work with our company.
Great, thanks, Bernard. Let's see, we have another one. Is this applicable in an indoor swimming pool area as far as humidity, and especially with respect to corrosive and chemical elements present in the sampled air?
Obviously, you need to remember always about the excessive humidity. So the use of the water trap is very, very important. The corrosive nature of I think we're talking about the chlorine. So at present we do not use so-called chemical filters. I am aware that from that kind of chemical applications, some people use it. But from what I've known from my experience, there was no danger or no risk of chlorine having excessive kind of damaging nature to our units, to be honest. But I cannot answer straightforward here because I don't know if we've ever tested it against chlorine impact on the electronics, for example.
All right.
But we've had it in swimming pools or leisure centers. So, and I've heard no troubles, no problems so far. So I can only presume that it works fine for years.
Okay, great. Another question. Is this setup similar to that of a duct detector or a sampling tube?
Well, the difference between the passive duct detector is that it relies on the flow of the air in the duct. The advantage of using the aspiration system is that it actively draws the air in. It draws the air inside of the unit, so it's much more effective and accurate. And from the performance point of view, it's much safer to use the aspiration system for ducts.
Okay. Properly sealed, can you use liquid ceramic installation coating?
So I presume that question was oriented towards freezer type compartment.
We might guess.
Yeah. Yeah.
Unless System Sensor has any specific guidance, I would say probably consult with the manufacturer of the freezer itself to make sure that the penetrations are protected as they recommend.
Okay, great. Let's see. In a high open area like an atrium, do we install the pipe up in the ceiling, or are there certain lower heights to cover stratification?
So, and that's a great question, and actually that same issue is applicable to things like waste transfer centers where you could have a thermal gradient. So the way I would answer that is there's a little bit of math that you have to do to figure out what is the potential temperature difference. So there's not a one-size-fits-all answer to that, but essentially there are some calculations. If you look in NFPA 92 or NFPA 72, they tell you how to do them to figure out if stratification could occur. And if that is a potential issue, then you would want to put make sure you have sample ports below the level at which stratification could occur. So no simple answer to that question. You have to do a little bit of analysis.
All right, great. Another question. Is a steam generating plant for heating and cooling a likely application for an aspirating smoke detection system consideration? High heat, high ceilings, high air movement?
I would think so. Normally, the aspiration system is very much recommended for high velocity air movement applications, because otherwise standard or traditional detection technologies might not be always able to actually pick up any smoke, thanks to the nature of the aspiration system, that it draws air into the pipe forcefully. Let's call it. It's most suitable for that kind of applications. On top of it, of course, when there is like steam or increased humidity, there are ways to deal with it by using the water traps or drip loops.
Okay. Another question comes in with a scenario. If there are 4 adjacent cold rooms next to each other, can I use a single aspirating detector for detecting smoke, or do I necessarily have to detect smoke with one aspirating smoke detector for each one of the cold rooms?
No, you should not use, by no means, you should not use the same or one detector because of the pressure differentials. You want to be sure that the air, because there might be a pressure difference in all of those cold rooms, so one detector per each cold room, each independent separate cold room.
Okay. Let's see. Can you discuss test ports? Several customers have asked for them. Are they required on each pipe or one per detector? How test ports shown on calculations?
What was the question again?
They just wanted you to discuss a little bit more about test ports. But several customers have asked for them. Are they required on each pipe or one per detector?
Oh, for testing.
Calculation.
All right, sorry, I misunderstood. Right, so technically, what you test on an aspiration unit is the functionality test, where you spray the appropriate can smoke into the last port on the pipe. It should be, if this is a branch configuration, it should be testing all branches, and depending on the class, is it the standard fire detection or early warning fire detection or very early warning, you have 120, 90 and 60 seconds respectively for this smoke to travel from the furthermost hole to the unit.
Okay. Any precautions if working in an animal food preparation plant? Too much dust.
Well, this is why we're so happy and proud about with FAAST, because our units do very well with harsh environments, even without the use of the external inline filters. I appreciate there is always excessive amount of dust, so the external filter, as we see it, is used more often as a kind of caution to advise the user of the excessive dirt in the pipeline rather than to protect the unit itself. So we're not saying that we should not use the filter, but it's just a reminder that, well, if you have the filter clogged, you should also clean the ports, the sampling ports, because they may get clogged as well. Don't forget that those sampling points are very, very small, or like from 1/8 of an inch and thereabouts, so they can clog with dust, especially when there is also humidity there as well. So cleaning and purging the pipes is also very, very important for system operation.
All right, great, thank you. So I want to be conscious of everybody's time here. I think we'll wrap that up for the Q&A. If there are any questions that we did not get to, we will follow up after the webinar. So on behalf of Honeywell Security and Fire, I want to thank you for joining us. As a follow-up, we will send you a brief survey and would appreciate your help in filling that out. Thanks again for joining us. This concludes our webinar. Have a nice rest of the day.
Thank you very much. Bye-bye.